I did modify the test a little bit since I last talked to you because there's a couple things I realized that I intended to put on that I was either tired or something I didn't put on. So I'm going to go over what those changes are. They're not really significant in some cases, but I want to keep you up. And so with that in mind, on number 2, I decided that the way I had that worded, it didn't test something I wanted to do, which is I want to have a mixture of something cold and something hot and find the final temperature rather than just the one that the way I had it all went one direction. So what I did instead is I rewrote this. I'll give you the one that I've rewritten, which is not saying that's exactly what you'll see, but it's very much like what I'm going to put on there. So I'm claiming that I have 0.5 kilograms of ice, all right, at 0 degrees Celsius, and I have 1.5 kilograms of water at 80 degrees Celsius, and I want to find out what happens at the end. Where does this all end up when I mix them together? Without necessarily looking at those, what are the 3 possible scenarios? Actually, in this case, there won't be 3, there will only be 2. What are the 2 possible scenarios that could happen? So I put a big chunk of ice into the water, and the ice completely melts, and we raise the temperature up. What's the second scenario? The water cools all the way down to 0, the ice does not completely melt. All right, do you see those are the 2 possible scenarios? What's the first thing I can do to find out whether that happens or not? What I would do is say, how much energy does it take to completely melt the ice into water? I write that number. How much energy would it take to cool this water down to 0 degrees Celsius? You'll both see how that's going to check out. In other words, let's think this through. If I find out the number for this, and I'm going to make a number up. It's not right. I'm making a number up. And I say that it's 100,000 joules to completely melt the ice. That's not going to happen with this thing. So it's not an answer, guys. And I find out that to cool this water down to 0 degrees takes 50,000 joules. What happens? What's the final state? If this, I need this much to completely melt the ice, but to get the water down to 0 only takes this much, what's the final state? There's ice and water, right? Because I don't completely melt the ice, only half the ice melts. Did everybody see that? All right. On the other hand, if this was the situation, now what do I know happens?
There's no ice.
All the ice melts and I have some temperature that's above 0. Everybody get that? So now using the numbers I've got here, somebody with a calculator, how much energy is available if I completely melt that ice? And if you don't remember, that's the latent heat of fusion for ice. And C for water. That's not there. That's sorry. That's just joules per Kelvin. All right. So, and these are numbers I would give you. And if you're here without a calculator, shame on you. Anybody have a number for the first one? 175.
No, 167.
Okay, 167.
50.
500. And that's joules. Okay.
And the other one is 6,000.
6,000?
Is it 1.5
Yeah,
Yeah,
1.5.
and then, yeah, then it's 6,000.
6,070.
Wait, no.
That doesn't seem right at all. Did you remember telling me to multiply the 80?
Wait, yeah, because it's mass times. Oh, no, it's NP.
So what you're going to do is you're going to take 0.5 times 3.35 times 10 to the fifth. What number?
The first one is right.
Okay, so this is the top now, right? What's the bottom? Where it's going to be 1.5 times 4,180 times 80.
It's 50160.
50.
1600.
So with this information, what happens? What's the final state? I mean, we don't know the temperature yet, but what's the final state? Ice and water or just water? Which one's bigger? This one goes, they're upside down, so this one goes up here and this one goes here.
Wait, which one goes to where?
Right. Ice melting, water cooling. These are the maximums. So this is bigger. That means that the ice completely melts. And then I find the final temperature. So there's 2 steps to solving this problem. First, I find out what happens. All right? Then I say, okay, here's what's the deal. I need this much energy to completely melt the ice. So how much does that energy cool this water? All right, the water cooling is where that comes from. How am I going to figure that out? Now I'm worried. This should be really straightforward based on the stuff we did in lab.
What was the question?
Yeah, what's the question? The question is, I need to completely melt the ice, so I need this much energy. So that's going to come from what's available from the water. So what I say is 167,500 joules equals MC delta T. In other words, the water's going to cool to give me that much, and I need to find out what the new temperature of the water is at that point. Right? The cooling water melts the ice. What's the temperature of the water when it finishes melting the ice? And I'm going to get it from here, right? Because I need that much to melt the ice, and that's going to come from the water cooling. So this is 1.5 kilograms times 4,180 joules per kilogram Kelvin times delta T. And you can just solve for delta T at this point because we know we're starting at 80. All right, so we just solve for delta T and figure out the new temperature. Does that make sense, guys? Everybody's good with that? So when I did that, and what I got was that delta T is equal to 26.6 degrees. All right, so that's how much I cool it. Gives me a final temperature. So I subtract that from 80, it gives me a final temperature of 53.3 degrees Celsius. But that's not the end of the problem. I've now cooled the water to this temperature, but what temperature is the water from melting the ice? When I melt the ice, it becomes water at 0. So now what I have to do is take water at 0 and water at 53 and find out where I end at the very end. What's the one thing they'll share at the very end of that problem? The final temperature, all right? So what I say is the following. I say the ice is 0.5 kilograms times 4,180, because now it's water, times T final minus T initial, which is 0 degrees Celsius. All right? This is what the ice is going to do. It's going to heat up to a final temperature, MC delta T, because it's water now. Talk to me.
So what was that one?
This one is how much the water cooled in order to melt the ice. So this was that ML sub F has to equal MC delta T. The melting ice has to get that energy from the water that's around it. So the water cools to melt the ice. And that takes the water to a new temperature of 53 instead of 80. So ice, water. As the ice melts, the water cools. Now the water is at 53, the ice is at 0, but it's water now. So I have water at 53 and I have water at 0. And they're going to find some middle point where they, at the end. So this is how much the ice water is going to raise in temperature to T final. And then it's plus 1.5 kilograms times 4180. I have units on that I'm not putting in, times T final minus 53.3 degrees Celsius equals 0, right? So heating the ice water and cooling the first water to the same final temperature, why do I say the total equals 0? What are those numbers, what do they represent in terms of physics concept? What is this number representing? Thermal energy, right? A Q, right? It's a Q. It's a heat flow in or out. This is a heat flows in, a heat flows out. And the total is 0 because there's no heat leaving or entering the system. All the melting is taking place just between the water and the ice. There's nothing from the outside coming in, nothing from the inside going out. They're just trading places in the ice water. Yeah?
So, 53.3 degrees Celsius, is that the final temperature or the initial temperature?
That's the middle temperature. So this is the temperature of the water after it melts the ice. So this is the temperature that I put here because it's my starting and this is my final. So final minus initial. So I don't use the 80 because I have to first melt the ice, which is what that gave me. Then I put this in. Now the only unknown here I've got is T final. And it's a little bit of algebra, but you solve for it. Does everybody see that I can cheat a little here and save myself some work? What's common to both terms? I can cancel it. So I have less math to do if I do that. It's not wrong to leave it in, but it's going to cancel. All right, so it makes it a little easier to punch numbers out. Yeah?
Could you explain TF minus?
So it's final minus initial, and when I melt the ice, what temperature is it? So it's going to go to T final, but it's starting at 0. And the water is going to start at 53 and go to T final. So it's always final minus initial, minus initial. The ice water is 0, the other water is 53. So when you put that together, so that you can check your work to be sure you're going where it goes, I got 39.7. Actually, I mean, you could say 0.7 or 0.8, it kind of could go either way, so just as long as it's around that. So this is the kind of problem I'm going to do instead of the other one. All right, so I'm going to have something, you know, it could be ice and water, it could be steam and water, it doesn't matter. What you're going to need to do is find out what's the final temperature. Just on a what if. What if I had a room full of steam and a cup full of water? What would you think is the final state of the system? So let's say the water, if the water's at 100 and the steam's at 100, what's the final state of the system? It's exactly the same, nothing changes, right? So I'm not going to go there. Let's say I have water at 50 degrees and I've got a bunch of steam. Steam is really hard to condense in terms of, there's a lot of thermal energy out there. So just almost on the blush of it, if I have a room full of steam at 100 degrees and I have a cup of water at 50, what's the final temperature of the system? It's going to be 100, isn't it? Well, what's going to happen is I'm going to have more water and less steam. But as the steam condenses, it'll raise the temperature of the water, but once it raises the water up to 100 degrees, I can't go anywhere else. All right? So say, for example, we had done this, and I came over here, and I found out the change of temperature was 80 degrees. What have I learned? That the water is going to cool all the way down to 0, and then I'm done. It's not going to melt any more ice than that. So sometimes you can have a final temperature that's 0 or sometimes 100. I'm not going there on this test. I'm going to rig the test so that you will know it's going to be a temperature in between the two, partly because I'm only giving you this question now. And the other one, they're a little, so they can be brain breaking. Now they're not, it's not so much difficult as bookkeeping. So I'm going to tell you, however I do this, I'm going to rig it so that whether it's steam or water or ice and water, the temperature will, I mean, all the steam will condense or all the ice will melt. I'm going to look for a temperature that's somewhere in between so that you can start with the assumption that all the ice melts or that all the steam condenses. Does that make sense? So it'll be 2 steps. The first step will be how much does the water's temperature change? And now I've got, it's either steam at 100 or ice at 0, and then what's the final temperature for those 2 kinds of water at the end? So it'll be that step. First step, find out which thing happens, and I'm guaranteeing you that all the ice will melt or all the steam will condense. All right, so at that point you just say, how much does the temperature of the water change as I change the phase of the otother part? Now I have water at 100 and this temperature, or water at 0 at this temperature. And I write an equation like this where all I do is solve for T final.
And to find how much it changes, you said that was 80 minus 20.
Exactly. So what happened over here, when I got the 2, I look at the smaller one and I say, that's the one that's going to happen. And it's going to be from here. So what I did is I said, this is what's going to happen to melt the ice, and it has to come from the water. So how much does the water have to change temperature in order to completely melt the ice? That's what I found here. If it had been steam, I would have put in whatever this number is. I'm still going to use this equation. So I would get this number from ml for steam, but it would be 2 point whatever times 10 to 6 instead of this one. Right? So it's the same exact process, you just use a different L. When you get there, you have to calculate both these numbers first to know. Although even though I'm kind of telling you that's going to happen, I want you to look at it because we need the number to be able to calculate the temperature change. So you get this from melting the ice or from condensing the steam. You're getting this from the water. To make the problem work how I want, this will always be the bigger number. So whatever number you get for the steam or the ice is the number you put here. And then you set it equal to MC delta T for the water to see how much the water's temperature has to change to completely melt the ice or completely condense the steam. Whatever that final temperature is, that's what you use here. And if this were steam, this would be 100 instead of 0. And then the T final is all you solve for.
So none of these questions might find it time to know.
No, so because what I'm going to do is, I changed 2 questions. I changed this one, and then I'm changing number 4. And the reason I'm changing number 4, I'll get to you in a second, Billy. The reason I'm changing number 4 is that the way I had it worded, I couldn't ask a different question, and I wanted you to have to think more. So I put something in there. Yeah, Lily.
So we always use the smaller number, you said?
Yeah, so when you get these 2, this says if the water cools to 0, I get this much. If the ice completely melts, I get this much. So clearly all the ice melts because before the water cools all the way to 0, I've gotten that much energy. I get the smaller number. So that tells me, looking at that, the smaller number tells me what happens. All the ice melts, and I'm going to have total pure water at the end. There's not going to be any ice. Or there wouldn't be any steam, whatever. Okay? All right. So that's the first change. On number 3, I'm making life just a little bit miserable here, but we're going to talk about it right now so you'll realize it's not that bad. But I need to test you on these concepts. So there's no numbers in number 3, but I'm going to ask you a couple more questions. So let me quickly draw the various paths. All right, so these are the 4 paths. What I'm going to ask you, in addition to naming what these paths are, this is number 3. So in addition to naming the paths, I'm going to want you to tell me whether the change in pressure, change in volume, or the change in temperature is positive, negative, or 0. All right? So let me actually put that this way. So the change in the pressure, the change in the volume, the change in the temperature, blah, blah, blah. All right? So let's start here. Name it first. Isochore because volume. I'm changing. Of course, the way I've done this is it doesn't make any sense without a graph, so we'll better give ourselves a graph. So it's pressure versus volume. All right, so isochore because volume is constant. Now let's do this. Is the change in pressure positive or negative? Positive because went up. Change in volume? 0. Change in temperature. Think of P equals nRT. All right, so if P is increasing but V is not increasing, T has to increase. All right, so it's a positive change for delta T. Good?
Can you do that? Can you repeat that again?
Yes, so take a look at it. If I have P equals nRT and I start here, V stays the same but P increases, that means the left side of the equation got bigger. Because V didn't get smaller, P just got bigger. What's the only number on this side that can change? T. So the other way to think of it is if I have an isotherm that goes through this and I have an isotherm that goes through this, that's clearly got to be a higher temperature. All right? Another thing I've taught you, anytime you have a vertical line up or a vertical line to the right, that's increases in temperature. All right? So now, as soon as you've answered this question, you've answered this question. I need you to know that. If delta T is positive, what's delta U? Because delta U only depends on T, so it's that easy. All right? But I need to keep that in track because if I come here, I know delta U is positive. Now, what's W? 0. And if delta U is equal to Q minus W, and delta U is positive, and delta U is positive and W is 0, what's Q? Positive. Do you see that?
How do you know if delta U is positive?
Look at your T. If T is increasing, U is increasing. Delta T is 0, delta U is 0. So because, remember, delta U equals 3/2 NR delta T. Those are constants. So if delta T is positive, delta U is positive. Straightforward.
Can you go over the Q?
Yes. So we have this equation, right? And what I'm saying is I know delta U is positive, so I write positive. On this one, I know W is 0. So the only way this equation can be right is if Q is also positive.
It's 0 because it's pressure.
It's 0 because there's no change in volume, right? So remember, the only way you can have work is if the volume changes. And work is always positive if I end up moving to the right. So let's take a look at the second one. This might help clear some things up. So delta P. Everybody see it? 0 because it just stays at the same value. So delta P is 0. Delta V, positive. Delta T. All right, and again, you can see this from here. If I have P delta V equals NR delta T, if P doesn't change and delta V is positive, delta T has to be positive, right? So we have a positive delta T, all right, and that, as soon as I write that, what do I know about delta U? It's positive, right? But now I have what kind of work being done? Positive. So I know that the work is positive. That's not where I want to do that. I know the work is positive. I know delta U is positive. And because I'm subtracting this number, what does that tell me about Q? It has to be really big positive, right? Because if I, let's look, if I have a number, Q, and I subtract W, and I still stay positive, Q had to be bigger than W. Does that make sense? Right? So I'm saying that even though I know that work is positive, but I'm subtracting it, that means Q has to be positive and bigger than W in order for delta U to stay positive. Is that cold? All right, so now let's take a look at first the isotherm. So on the isotherm, first let me establish both the isotherm and the adiabat. What can you tell me about the work? It's positive because there's area under it and it comes to the right. So the work's going to be positive. We'll get there in a second then. Now looking at this, going from A to B on the isotherm, does P increase or decrease? It decreases because it's down, right? So P is negative. B, positive or negative? Right, it's going to be positive because I'm going to the right. So P is negative because it goes down, B is positive because it comes to the right. Now, I said it was an isotherm. What does that tell you about delta T? 0, right? What can I immediately say about delta U? 0. And what we then have is the Q and the W. We already established just looking at this that W is positive, right? So what does that tell me Q has to be? Guys, don't go there, don't go there, don't go there. Look, delta U is equal to Q minus W. 0 equals Q minus W. Q equals W. If W is positive, Q is positive. If W is negative, Q is negative. Now, this is assuming that Q is the heat that flows into the system and that W is the work done by the system. And as you saw in your homework, sometimes we can flip the words on that. I am not flipping those words on this test. During the homework, you had to do some flipping. I will not play that game on you because this is a much more standard form of this equation, so I'm not going to flip it. So it will always be Q is the heat into the gas, W is the work done by the gas. And I will actually write in and by to help you remember that. Okay? So this has to be positive as well. Now, for the adiabat, both of these are the same, aren't they? For the adiabat, pressure still decreases, the volume still increases, but the temperature decreases because it's below the isotherm. So I have a decrease in the temperature. Yeah? So delta U is also negative because whatever delta T is, delta U is. And we just established that the work was positive, so this is very rigged and I'm hoping you'll see it. What's the name of this path?
It's
Adiabat. And what is an adiabat? Q is 0. That's what an adiabat is Q is 0. Yeah.
How did you find delta T?
The way I found delta T was I looked at an isotherm and I noticed that I'm below it, which means I have a lower temperature. So like I say, there's no calculations here, but this is a way that I can check to be sure you've understood all the various quantities that we talked about in this chapter. You're telling me that makes your head hurt, Holly?
Yeah.
I'm somewhat sympathetic, but I'm the teacher, so I have to make you suffer. All right, we don't get to.
W is
How did you
positive.
And just let me call on people so I can keep it in order.
So why is word positive on
Okay, the reason work is positive is that you look at the picture, I look at the area under the curve, and I come to the right, so it's positive. And who was next? Okay, go ahead, Ron.
W is positive, right, on this one?
W is positive for both of these because, look, as you look at the area under the curve, it's increasing as I go to the right. The area is getting bigger. And yes?
And then mine is how did you get a negative? Oh, never mind. Got it.
Work? Anybody else? All right, so I hate to be this much of a pushover, but that's probably exactly what I'm going to ask you on this problem. So your job is simply to understand that well enough to reproduce it. Okay. Kid, is that a halfway up question or?
No, we're good.
It'd be just like, you wouldn't have numbers or anything.
No, that's why I call it a concept question. So this is very much testing your concepts, your understanding of the ideal gas law and the first law of thermodynamics. This is my way of making sure you understand both the ideal gas law and the first law of thermodynamics, which is this equation and this equation. Putting those two together.
So you're changing, for number 3, you're changing D to this then?
Right.
So we're not doing one.
Right. We're not. We're not.
Okay, which one's?
I don't actually, you know what? I don't have a copy of my old test anymore. You know how I asked you B. Yeah. So this is the new B.
Okay.
So cross out this one.
Yeah. Cross out that. Yeah.
So for your isobar, it's your T is positive, but your U is
Also positive. Anytime you know T, you know U.
um,
Delta T and W are always exactly the same because of this relationship right here.
yeah.
W equals 3 has NR, all positive numbers of delta T. So if delta T is positive, delta U is positive. If delta T is 0, delta U is 0. Right. Guys, we good? All right.
Okay, so for number 2,
Uh-huh.
I just want to verify, that's gonna be our number 2.
That's the number 2.
So don't put it,
Yeah, don't worry. Yeah, don't do this and do this one. That's why I wanted to get
practice
you.
that another.
Exactly.
Are you also changing number 4?
I am. But again, it's not a big change. It's just that it allows me to ask some of the questions I had on the old number 2.
Or the actual bar, he has to be a positive number, right?
It has to be bigger than W. Maybe not necessarily really big, but it does have to be bigger than W. Otherwise, W wouldn't be positive. It has to be positive. Why?
In order to make
Also because the temperature increases, so W has to increase. Right, so it's those two put together. All right, so write really carefully because I'm not going to change much other than the numbers. I want this to be a really easy test to grade because coming back from Thanksgiving, I don't want to have to sit. No. All right. So basically, here's what I'm doing. I'm saying about a hot plate. You don't know what a hot plate is, right? Nobody here's poor enough to have ever had to live on a hot plate instead of a stove. All right. So a hot plate is just the way poor people like me used to cook food when we were. This is number 4. Right? So I have a hot plate that has a temperature of 250 degrees Celsius, which I went online and checked, and this is a typical number for a hot plate. Okay. So my first question is, would I be able to boil water with this hot plate? Yeah, right? Because I just need to get it up to 100. So this is going to be good. And it delivers 700 joules per second. All right. So I've got this. So I'm going to get the rate that we had that was in number 2 before here. All right. So I've got a hot plate, 250 degrees Celsius. It's going to deliver at this rate. And I have 1 kilogram of water at 100 degrees Celsius in in this pan, all right, on this hot plate. So it's in a pan on the hot plate. And I'm going to boil the water completely away to steam. Salud. All right, so here's the question. I want to find entropy changes. So go on. Remind me what entropy equation we have to deal with in this class. Q over T. One of the things I need you to understand, guys, is entropy, is this a state or a process in this equation? It's a process. How can you tell just by looking at the equation? Because Q is always a process. Right? What are the two things I told you always depended on path? Q and W. Q and W are always paths, not states. So this equation tells me that although entropy, there is such a thing as a state of entropy, with this equation I'm talking about a process because it's defined in terms of Q. Right? So what we want to look at is the entropy changes that occur in this system as I boil the water completely away. What are the things involved in this system? What are the things what's the universe as far as this process goes? Hot plate, the water. Any real cooks in here? Is that enough to boil water? Hot plate and water? The pan. All right? So here's the deal. I mean, play the game just like real life. I mean, this is what, if physics doesn't work with real life, we're not doing it right. So yeah, I've got to have a pan. Okay? Now, in terms of energy flow, does energy flow out of the hot plate? Into the... Yes. So that's going to be one state. We've got a Q for the hot plate, and it's negative, isn't it?
Yeah, it's all the way down.
Right? Heat flows out of it, so it's going to be negative. Does any... This is, I guess, a little tricky. Does the pan have a net entropy change? In other words, the question is, does any heat flow into the pan that doesn't flow out of the pan? If that were true, what would be happening to the pan? Its temperature would be increasing, wouldn't it? And wouldn't we say at some point that's got to stop? Because if it didn't, the pan would melt. And the pan doesn't melt. So it's really a little bit like the rod we had on the other problem. Any heat from the hot plate that goes into the pan either radiates to the environment or goes into the water, but in any case something happens so the pan quits changing temperature. And it doesn't change state. So the entropy change for the pan is 0. Does that click?
Can you say insulated pan on the question?
No, I don't want it to be insulated because if it were insulated I couldn't boil my water. So, I mean, if it were insulated, that's like I did on the other one, that was fine. But what I wanted to do there is I didn't have any way to know how much heat flowed into the other reservoir, so I insulated it so I knew that everything that came out went in. But here I'm going to know because I'm telling you I'm boiling the water completely away, so I really don't care. All right? And by the way, here's what I'm saying is delivered to the water. So what happens is this hot plate might be delivering more energy than that, but it goes to the environment. This is the amount that actually gets delivered to the water. So the other thing is, given our class, I can't have any processes where I ask you to calculate entropy unless they happen at a constant temperature. Does the hot plate stay at the same temperature? But just give me, I mean, you're nodding and that's good. Give me kind of a sentence you can explain to somebody else to say why that has to be true.
Yeah, at some point it has to be like...
If it's changing temperature, it's going to have to stop, because if it doesn't, if it just keeps increasing forever, it melts the world down, and if it decreases forever, it's not going to boil water. So it has to hit a point where it quits changing. All right? How about when I'm boiling it, does the temperature of the water change?
Until it hits 100?
No,
Or is it already-
because I get to 100, and once I get it to 100, it begins to boil, but it boils at 100, so there's no temperature change. And so I'm playing fair with you, because we can't calculate this if the temperature's changing. So the hot plate's temperature doesn't change, and the water's temperature doesn't change, and I have everything I need to calculate all the changes in entropy for the three things involved. The hot plate, I've given you the temperature of the hot plate, right? And I can figure out how much heat has to flow out of it in order to boil this much water. So then I can find that Q, and I can put in the temperature of the hot plate. Does that make sense? In other words, how am I going to get the Q? Because I'm claiming that the Q that we're interested in is actually going directly into the water. This is where your insulation might work. We insulate the sides of the pan to make sure it all goes directly into the water. So there's a bit of a slipshod statement here, but we're going to live with it, okay? So now, how do I find the amount of heat that it takes to boil this water? I've got 1 kilogram of water, and I want to boil it. What's my Q that I need to do this? Am I changing temperature or am I changing phase? So we had a lab on Monday, which should have made this really clear. Guys, you've got to have these. You've got to have these. If I'm changing temperature, it's MC delta T. If I'm changing phase, it's ML. And L is either fusion or vaporization, depending on whether I'm freezing, melting, or boiling, condensing. ML is changing phase. MC delta T is changing temperature. My water is at 100 degrees and it's boiling into steam. So it becomes 100-degree water going to 100-degree steam. No temperature change, so I would use this. And so again, we would need, it's the 2 point whatever it is, 2.256. Yeah. We'll get there in a second. So for right now, it's just to confuse us, but we'll use it in a second. So does everybody understand that I can find the amount of heat that it takes to completely boil the water? Because I've got 1 kilogram, that's my M, and I've got this L, I can find a number, all right? And now that I have that number, that represents this Q. With that Q, to find the entropy of the boiling water, I take that total Q that I just calculated and I divide by what number? You would get it wrong. 373. It has to be Kelvin. And so it boils at 100 degrees Celsius, so you've got to remember, you've got to make it Kelvin. Right? So that temperature has to be in Kelvin. So you're going to have to add the 273. Yes?
Where'd you get the 2.256?
I looked it up, actually. You'd be given that. And any constants like that, I'd always give you. So that's a heat of vaporization, I would always give you stuff like that. I'm not going to ask you to memorize stuff like that. In fact, you saw me, I had to look down at my paper, I don't remember. I knew it was 2 times 10 to the 6, but I didn't know the rest of the numbers.
So what would be an example of LB, or of the water condensing, or what?
So if instead, what I had done was I put steam into, here's a wicked problem. So I have ice and steam, and I put them together to find out what's the final state. So I would use the condensing, the ML, because the steam is going to condense to water to heat the ice. And I'd have to balance to see. I'm not asking this question on the test. It turns out that it's harder than it needs to be for a test. It just becomes tedious, not difficult, just really long and tedious. Because you'd have to find out how much of the steam needs to condense to completely melt the ice, and how much of the steam needs to condense to raise the temperature of that ice to some, and you just have to play the game. And it's just long. It's not necessarily informative. So, but in this case, I wouldn't need to condense because I tell you I'm boiling the water. On the other hand, if I had steam and ice, then I know that the steam is going to condense to melt the ice. So it just depends on which way the heat is flowing. All right, so I'm claiming that heat flows out of the hot plate at 273 plus 250, right? Everybody understand what that fast talk was right there? Remember, this is Celsius, and I always need Kelvin in this equation. So I'm going to have to add the 273 to it. All right? Now, I find the Q from this, don't I? This is the amount of heat that came out of the hot plate. It went into boiling the water. So whenever this mass of the water, 1 kilogram, times this number here, so if it's 1 kilogram, this is really easy. 2.256 times 10 to the 6 is the Q. Right, so that's what will go up on the top. And on the bottom, I tell you that the hot plate is this. So the amount of heat that comes out of the hot plate is exactly the amount of heat that goes into the water. So it's the same number, so it's the same Q. This part is no different than the question I asked before.
So we only have to find, right?
Exactly.
Because the other two stay at zero. Or, I mean,
No.
not stay at zero, they are
No, they're going to be different. The Q is the same, but the temperatures are different.
zero. Wait, can you go, what did you just
Yeah.
find?
So I said the Q that boils the water completely away is equal to 1 kilogram times L, which is 2.256 times 10 to the 6th joules per kilogram. Kilogram cancels, and I've got 2.256 times 10 to the 6th joules is my Q. And that's for both the hot plate and the water.
So
Because that comes out of the hot plate into the water. Right?
So we're trying to find the entropy of the hot.
The whole
plate
point is just
and-
to ask to find the entropy. So, for the hot plate, this is 2.256 times 10 to the 6th joules, and the hot plate is at this temperature, yeah, I wish I could do that in my head. So it's 523 Kelvin. Right? I just added those two numbers, that's the temperature. And then for the water, and by the way, that's negative, right? Because it flows out. And then for the water, it's 2.256 times 10 to the 6th joules over 373 Kelvin because it's at 100 degrees. Which of these numbers is bigger? Yeah, and goes in. So this is the, so what happens when we add these, I get a smaller positive number and a larger negative number. I mean, it's a larger positive number and a smaller negative number for a net positive number. Does that make sense? Did everybody see why this is a smaller number? Because I'm dividing by a bigger number. So this is a small number, got a small negative and a larger positive. I add them together, I get positive. And remember what I said is in any closed system, entropy changes can never be negative. They can be zero if nothing happens, but stuff is happening here. So the fact that it turns out positive makes me happy because what's one of the rules of the second? One of the ways we can say the second law of thermodynamics. The entropy of the universe always increases.
How is Q the hot plate equal to the Q of the water?
I really wish I had asked that question. We're assuming it is, and I'm going to tell you to assume that.
Okay.
Because it actually isn't, there's going to be some loss out the side of the pan, but I'm assuming that's a negligible compared to everything that's going on. So it's a good question, but it makes the problem impossible, so we're going to pretend like it didn't happen.
So are you gonna add the entropy for the hot plate and water at the end?
Well, I would suggest that if you can't see it, then yes, add them to show yourself that it's positive. So, yeah, so you've got to give me some kind of an argument for saying, is it positive or negative? So if you're not sure by looking at it, just add them. You just calculate it, add them, and say, oh, when I add them, I get a positive number, or I get a negative number, and I need to start over.
So are we gonna do this all in one, like is it just gonna be one problem, or is like problem A gonna be find the entropy for the hot plate?
The way I got it set up is, I said, the first question I asked is the entropy of the pan changing?
Yeah.
The pan.
Oh, the pan, no.
No, it's like just the conduit through which the heat flows. What's the entropy change for the hot plate? And I said, you're going to need to find the Q to boil that much water, and the heat of vaporization is this number, and I give it to you. All right? And you know the mass of the water, so it's just ml, right? But it's negative. That's what I need you to say. It's negative because the heat from the hot plate is flowing out of the hot plate. Then I say, what's the entropy change for the water? It's the same number. Well, not the entropy change, but the heat is the same number, but it's got to be positive. And the only difference, guys, is the hot plate is at 250, but the boiling water is at 100. And you've got to add 273 of both of them to get it into Kelvin. All right. So then the last question is it's basically the same stuff I had before, but I changed the process. So is this consistent with the laws of thermodynamics? And the answer is yes, because we need entropy to increase. And Juan, did I scare you to death?
I'm good.
Okay. All I'm seeing is ringing in your, no.
Or are you saying that the entropy for a hot plate is gonna be negative just because heat needs to
Flows out. And the entropy for the water is positive because heat flows in. All right? So, now on number 5, so before I go, so any questions on those 3 things?
The last part, you said to add them.
Yeah, you can just add these 2 numbers to find out what the total entropy is, all right? And this one's negative and this one's positive.
What do you want us to state after that?
What I'm asking is, if you get a negative for the hot plate and a positive for the water, and you add them and you get a positive number, that tells you that entropy increased for the universe. And therefore that's consistent with the laws of thermodynamics. On the concept questions, I mentioned it in passing, but I want to be sure you understand. In addition to the ones that I specifically gave you, I said there's one other question that would be possible. I'm not promising. Remember I said, why does sweating make us cool? Why does sweating cool us down? All right, and that's a possible one that was not on the thing, and that I mentioned that last time. I'm not sure if you got it in your notes. So I asked, why does sweating cool us down? What?
Similar to a heat engine.
No, it's actually much simpler. The thing, so somebody want to help him out there. What's the first thing I suggested drawing when you're trying to do this? If I'm trying to show why sweating can cool me.
Due to the heat flow of a small mass. Is it? Those things, they're too small, so they leave really fast. And then what you have left is the cool one.
Right, so what happens is, anything that has a particular average kinetic energy, which this line represents, has things that are cooler than that and has things that are hotter than that. There's actually a point at which water boils. All right? So what that means is anything hotter than that does what? It boils and leaves the system. We call it evaporation. All right? So it evaporates, and that means this goes away. Now, if you're averaging things and you get rid of your highest numbers, what happens to your average? It drops. And so that means that my VRS drops, which means my temperature drops, which makes me cooler.
What are the axis labels?
This is the velocity. So if I'm having the velocity versus the number of atoms. So this is not a big deal. It's not a big deal. It's just a way of keeping track. It says most of the atoms have this. I mean, this is the most common speed. This is the average RMS speed. The average speed is here. I'm not going to worry about that. There's 3 lines. But the main thing you just need to know is that there's some point beyond which this velocity is associated with a boiling temperature. Remember, because we say atom per atom, so that the kinetic energy of an atom is equal to 3/2 kT, which means if I have a higher V, I have a higher T. So really high velocities can have a temperature so high that they boil and they leave the system. Because when you boil water, it becomes vapor and leaves. That lowers the average temperature and I feel cooler. But immediately my body heats that back up and even more boils away. So what happens, I have to dump heat into that fluid to heat it back up after it cools. And I sense heat flowing out of me as cool. Remember, we don't exactly detect temperature. By the way, here's an experiment. If you want to do this at home, really easy to do. I may have mentioned it. Get 3 bowls of water. In one put cold water, and the other put hot water. Don't cook yourself, but make it hot enough that it feels hot. And in the middle put tepid or lukewarm water, just kind of in between the 2. Stick one hand in the very cold water, one hand in the very hot water. Leave them there for a while until you get used to it. Then put both hands in the lukewarm water, and your brain will tell you that this hand is in hot water and that this hand is in cold water, even though it's the same bowl of water. Have you done that before?
Well, because I've woken up, have been in, come out and it's really cold. When you take a hot shower, it
almost hurts.
yeah.
Yes.
But it's not like
It-
burning hot.
Well, haven't you ever had that? It happens to me actually every morning. I get in the shower. First, the water feels too hot, and then after a while, it's not hot enough. It's the same water. It's like, again, it's how rapidly the temperature, the energy flows in or out of my body. All right, so that's the other question on the concept questions. And, yeah, go ahead, I saw several hands.
Are you just gonna ask us about the greenhouse effect still?
About which?
The greenhouse effect?
You know what, I forgot about that. And it honestly compels me to say, although it's really important, it didn't make the test.
What will happen at the other extreme of the,
What happens down here?
yes.
Basically, I mean, there's nothing particular that happens there because we've got this average going on. So all that's happening is that when this goes away, it simply shifts the average. And the average is what I feel.
I mean, on the other side of the graph.
Over here.
Yeah,
But what I'm saying is nothing.
okay.
So what happens is, as this goes away, what happens is the graph basically does this, which puts my average down lower. But what's really happening is this is all happening instantaneously, so there's really never a shift like that. As soon as the fast one goes away, my body dumps heat into the water to try to raise it up, and that's what I feel is cooling. That's why sweat cools me, is that heat's leaving me to try to raise the temperature back up. Yes?
Can you repeat that one more time?
Yes. So all gases, all substances, the velocities associated with a given temperature are actually in something we call a Maxwellian. They're not just one temperature. They're a whole range of temperatures, a whole range of velocities. That means that in any given situation, especially like you have a liquid, some of the atoms in the liquid are moving fast enough to leave, which is basically boiling. So when they leave, the ones left behind have a lower average. So that feels cooler to me. All right? So the average is what I sense. That feels cooler. Two things happen. I feel cool, but then my body heat flows out of me to try to raise that temperature back up. So I'm cooled at two levels because the liquid touching me has a lower average, and heat is leaving me, which I always interpret as cold or cooler. Yes?
The average, what?
The average velocity of the atoms left behind is lower. And that's associated with a lower temperature. Because from this equation, the speed ties to the temperature. So a higher average is a higher temperature, a lower average is a lower temperature. Yes?
You still planning on testing this on thermostat design?
Thermal which?
Thermostat design, can you mention that in passing? So that could be a potential next question. Thermos or
Yeah, that's number 5, we're getting to that. Yeah. So, and yes, that's again another guarantee. Number 5.
So how does this work?
So when we sweat, that puts liquid on our skin, right? Sweat puts liquid on your skin, and this is a map of the velocities of the atoms in the liquid. And so some of them boil away. The fastest moving ones literally boil away, lowering the temperature of my sweat, making me cool. I'm not all that cool. All right. Okay, so number 5. Name the 3 forms of heat transfer, define them, and explain how they work to make a thermos bottle. So what are the 3 ways that we can transfer? Actually, there's 4, but I'm doing 3. Conduction. Convection. And radiation. Conduction is transfer by contact. What was the example I gave in this? Put a spoon in a flame, right? Now, while I'm holding the spoon in the flame, my hand gets hot because the heat transfers through the spoon. I'm in contact with the spoon. That's what I mean by contact. Stick your hand on a hot stove and contact. You'll never, yeah, please don't go do this experiment. But yeah, that's contact, that's conduction. All right? Convection,
Due to moving fluid.
all right? Heat transfer from, so transfer due to a moving fluid. How did your grandmother keep herself cool in church?
Has a fan.
She had a fan, right? And she would do this. Why does that work? A moving fluid, there's a fluid. So what happens is, when I sit perfectly still, I'm radiating heat, and that warms up the air all the way around me, warmer than the air that's further from me. So when I do this, I push aside the air that I've warmed, and I put back air that is a cooler temperature. And that anytime that the gradient is larger, the heat transfer is larger, so that allows me to cool more rapidly. Yeah?
I thought it actually didn't work though, like, doesn't it actually make it like hotter?
Yeah, I've heard people argue that because of the exercise you're actually heating yourself up. This is why you now go with the electric fans and turn the switch and they do it all for us. But actually, I'm here to tell you, this works. And the fact that it works means that whatever person is explaining it that way is wrong, because clearly if fanning didn't work, people would stop doing it. It's been through thousands of years that it's worked very well for people, even if it was the pharaohs having other people doing the exercise to get the fanning. But fanning does work. It does work. But does it always cool to have convection? No. What's an example of something where it actually makes it hotter or makes it more efficient? The heat transfer. Y'all ever heard of a convection oven? The whole idea of a convection oven is that one of the things that slows down cooking is in an oven you put stuff on the middle tray and all the heat goes to the top of the oven. In a convection oven you have fans that drive the hot air all the way through the oven and you cook faster because it gets the hot air back down to the food.
Absolutely.
Right?
You can go to the sauna and sand yourself.
And does it cool you?
No.
Yeah, so again, what happens in a sauna, because of the fact that the air around you is hotter than you are, fanning simply moves the hot air back in. All right, so that's not going to work. And yes, thank you for reminding me that everything is more complicated than I wish. All right, and then finally, guys, the radiation. Yeah, so transfer through electromagnetic radiation. All right, I don't. You've heard me say it. We're going to say electromagnetic waves, but that's really just a dodge. What kind of electromagnetic waves do I emit? Infrared. And that's why you have night goggles. Why do night goggles work? They don't work so well in the daytime because the sun heats everything up pretty much to high temperature. But at night, when everything cools down, warm-blooded animals don't. So what happens, night goggles can see the infrared coming off of anything that's a warm-blooded animal. That includes people. All right, so that's the basic idea behind night goggles.
So then you would be able to see like snakes and stuff.
Not after they basically cool down to the ambient temperature, because if you could see them, cold-blooded animals tend to cool to ambient air temperature, and so if you could see them, you'd also see air, and then your screen would be white, and that's kind of useless. All right, so yeah, typically cold-blooded animals we don't see. There are times, if you were in a room and you suddenly turned the lights off, you could see them until they cooled down. All right. So are we good with these three things? There is a fourth, which our book says evaporation. But for me, evaporation is the thing I just told you about in terms of the Maxwell thing. I don't see it so much as a direct form of cooling as it's kind of a combination of several of these. The thermos bottle. The basic idea of the thermos bottle is it's a bottle within a bottle. All right, and actually I did that badly. Let me redraw that because how the real thermos works is different. And you did this in lab, so you should be good with it. The basic idea of the thermos bottle is it's a jar within a jar. And the place that the two jars hook together needs to be a bad conductor. In our lab, remember we had that little, I call it phenolic, I don't know if you ever heard of that. It's kind of like a pressed board or something, all right? So it's clearly not metal. It's kind of a wooden looking stuff, and that's not a very good conductor. So that basically insulates the inside jar from the outside jar, right? So which of these three is that? That's getting rid of conduction, right? So basically we don't let this touch anywhere except for right at the top, and where it touches at the top, we make sure the only thing it touches is a bad conductor. And that means it's not going to have much conduction going on. Now, convection, if I just had the jar like this, what's the problem? Ambient air goes past the sides and it can cool it down, and as it cools it down, then the contents would also cool. By putting it inside and then making this a vacuum, I don't get any moving currents because vacuum doesn't move, right? Vacuum's nothing. So there's no way to get moving fluids on the outside of this to cool it down. But there is on the top, right? Air can blow past the top of this, so there's a duh moment here. What's the other thing we do to get rid of convection? We have a lid, all right? And I know you think the lid is to keep it from spilling. but it's a twofold invention. So it keeps it from spilling, but it also keeps